I can start. Um, my name is Javi Fontán, and I'm engineer in Sourced. I'm going to present you a project that we are doing in the company that's called Gitbase. That is a SQL interface to Git repositories. And does any of you doesn't know anything about Git versioning? Or I suppose you don't know anything about Git? You do know. Okay. So it's going to be easier for me then. Before talking about Gitbase itself, I'm going to talk to you a little bit on what we do and why we need it, and what were our first steps before doing that. The company Source, what we do is basically we do open source tools to do large-scale analysis on source code and machine learning. To do that, we need to retrieve a huge load of data, a huge load of Git repositories with source codes and so on, and then process them. Basically, the main workflow that we do is that we download right now. We are downloading all the public repositories that we can find. This means that all public Git repos, or Bitbucket repos, Cgit repos, etc. That's what we're doing right now. And then with all those data, we extract some information from it. So if there's some things that we do with this data is, for example, getting files that are similar between several repositories. We can find files that are the same one that are copied by the developers, so we can grasp this kind of stuff. We will also find licenses of projects. We can automate this stuff, and also we can find which languages a programmer was using on its lifetime or inside the company. So if you want to see more or less how is the pipeline in a more graphical way, in this example, we are downloading repos from GitHub. We store it in a local storage in our machines, and then we have this process box. This is where most of the attack will be, because Gitbase is going to be there. In this process, we do several things. We do searches on the data that we have here, and we also extract some information from it. Things that we do, that we extract, and we need to do some analysis, is detecting the language of source code, so we know what it is, and we also extract UAST. UAST is something done in our company. It's called a universal AST. Basically, is the tree of the source that we have, but modified so you don't need to know the particularities of a specific language. So you can search for functions in JavaScript and Go with the same code. You don't need to understand both languages. After that, we do some other processing on what we extracted from the data. We do several things with it, and one of them is feeding it to AI. So, for example, we can do things like automated code reviews and things like that. So how we do this at this moment? We have a project called Engine that is a Spark library to do extraction, find data in the Git repos and extract information from it. And it's like the framework that our users are using to extract and also analyze that data. This can be used from Scala and also from Python. So you can create a Scala application that goes into Spark to do this analysis. But you can also use, for example, Jupyter notebooks and use Python to extract this data and learn something from this data. You can also use Spark SQL queries to get it. This engine has some dependencies. The first two ones are created in our company. It's Entry to detect the file language, and also Bubblefish, that is the one that generates this universal AST that we use to analyze the source code itself. We also use JGit, that is the library that is available for Java and for Scala also, to read the Git repos and extract the information that we need. This is an example on what we do right now. It's in a Scala example, and it's using the engine library to find some repositories with a filter and so on and so on. The current architecture of how the workflow that we do is done in a Spark cluster. It's a basic Spark cluster. The only thing that you have to know is that we have all the repos are stored in HDFS, so each worker has like a set of Git repos that are analyzed on each of the workers. So why are we thinking and why are we doing things if we already have this framework working? The thing is that this is working pretty nice, but the thing is that sometimes we don't need to analyze that huge amount of repos, and we don't want to have a dependency on a Spark cluster to do some small queries. Or if we are creating another software that needs to extract information from it, and if the dependency of this Spark cluster or Spark itself is that big, maybe people are not going to use it because they have to deploy Spark for some reason that it works. So what's exactly Gitbase? Gitbase is MySQL compatible server to create Git repos. That means that you provide the server with a set of a directory with a lot of Git repositories. Then you connect to it with a MySQL client. This means that you can use the command line interface of MySQL, for example. It's compatible with it. It's written in Go language. This has some nice features. Like, for example, we compile an almost static binary that you don't need to install a lot of packages and so on. So you just put the binary in the server, fire up the server, and that's it. And also it's Apache license, so it's open source. You can just download it and change the code if you want, etc. Basic run of Gitbase. To start, you just provide a directory with the Git repositories. And then, for example, with the MySQL client, you can connect to the port that it opens, and you can start sending some queries and get information just as a normal MySQL database. This is a very simple query. What I want to show you here is that this is a normal query. This doesn't have anything strange to get things from Git. You just have a set of tables with a set of columns, and you just do a search, and you get the results the same way that you would do with MySQL. So why we did Gitbase like this? One of the reasons is that we already had a Git library written in 100% Go in-house to do. We mainly use it to download all the repositories. We use this library to do that. But we can also do that to query these Git repos. So all the experiences that we have with the library can be also moved to querying the Git repos. It also allows us to do things that other libraries cannot do, and we can make it faster and store information that maybe others cannot do. The other thing is that we wanted the server to be very, very easy to deploy. That means that it won't be only used on big clusters in a lot of machines and big item machines and so on. But you can also deploy it in your laptop if you want to do some queries on, don't know, which is the biggest repository or the one with more commits and so on. The other thing is that we wanted it to be SQL. We use a SQL flavor because it's something that a lot of people already know. So they don't need to learn other ways of extracting data or filtering data. They can just use the SQL that they already know. The other nice stuff is this MySQL wire protocol compatible. That means that we don't have to create any library for any language to connect to it. It's already compatible with Java because you already have JDBC to connect to MySQL. It's already compatible with R. It's already compatible with anything that has a library to connect to MySQL. And also the good stuff is that we can connect with Spark. So we are not ditching the previous architecture. We are just swapping some components. Probably you are thinking on why don't you just cram all this data into a database and forget about creating this project. The thing is that Git format is very, very space efficient. It's super efficient in that. It duplicates a lot of stuff, and it really is really good doing that. If we wanted to do that with, for example, a MySQL database, maybe this could grow in the 10 times more space than is needed. The thing is that we want to process all public repositories. So, for example, you can be thinking on 60 million repositories going from some kilobytes to some gigabytes, and you can think on how big this will be. The other thing is that if we put all this data inside the database, we will need to have a preprocessing step. We need to get the Git repositories, extract all the information, put this information inside the database, and then we can do the queries. But we don't want to do that. We just want to go into the data source and extract information directly from it. So there's not this previous step to start working. This is internal architecture, how it's made. The first box here is Vites. That is a project by Google. It's a clustering for MySQL, clustering project for MySQL. And from it, we use the SQL parser, so it's compatible with MySQL, and also the MySQL write protocol, so it's also compatible with it. Then we have this Go MySQL server that is a project from us that is the engine of the database. It's the one that knows how to do the joins, how to do the sums, how to do the count, etc. But doesn't know anything about the storage. It's storage agnostic. So if you want to create a new database that instead of talking to Git talks to, don't know, LDAP, you can do it with that and just create the storage implementation that knows how to retrieve this information. And then we have Gitbase itself that also uses has some dependencies. You'll see that from the previous slides, we've changed JGit to GoGit. Now it's a Go library. But we are still using Bubblefish and Henry to detect the language and also extract the tree of the source code. Then we have the Git repos that Gitbase is written. And for indexes, we use Pilosa, that is a bitmap index server that we use to do the indexes. And then we use VoltDB to do the mapping between values and positions in the bitmap. Because in the bitmap, you only have positions, and we need to know what they mean. Internal, we use a Volcano or Iterator model. It's only one database that has all the repos. It's not that we have one database per repository. We cram all the information that we have from all the repos in only one database. We have like two kinds of objects. One is the objects that are almost one-to-one relation from the Git object to the table. So you have the same information in Git and in the table. And then we have some special tables. We have the relation tables to know that this commit belongs to this repo, or well, this file belongs to this commit and things like that. So you don't need to do a lot of jumps to know these things. And another table that makes easier to work with files, but that's mostly it. Other thing that we add is the functions to do things or to extract things that are not inside the Git repo. That is the language and universal AST. Basically, well, this is a rough graph of iterator model. What it means is that every node in the logical plan is an iterator. So everything has a next, and you can extract the next row. So in this case, we have two tables. The tables have a next method that you can extract the next row. So give me the next one. The filters, the where is they are the very same. It's an iterator that when you call next, it gets the next row from below that matches the filter, and the same with join. An interesting part here also is the dot line, and you can see the difference between Gitbase project and Go MySQL Server. Go MySQL Server knows how to do filters, how to do joins, how to parse the SQL and all that stuff. And Gitbase is providing the storage layer that knows how to extract the data from Git in this case, but could be anything. Yeah.
When you say about the storage layer, you mean that you are just reading the data because you are not storing anything new in addition to the repository data. Is that correct?
Is that correct? That's correct. These are the tables that we have in Gitbase. If you've been working with Git, probably you know some of them. For example, commits, it's something that you know what it is. Blobs is also the contents of files. So everything that you see here, this is terminology from Git. This is objects that are already in Git. These are the other tables that I talked to you before, that we have some relations. So we can relate trees, that is, file trees, with commits, blobs with commits, references, and so on. And then we have these files, that is a special table that makes it much easier for someone to extract information about the files from a commit and so on, instead of going through all the relations that you have there. So this is nice, this works. You can do queries, you can extract information from it, but it's not the fastest database ever. We have some problems in that. One of the biggest problems is that I told you before that Git is super good storing things, but when you want to retrieve things from Git, this is not that nice. So one of the ways to make it faster is only get objects that we really need and not to go through all of them and waste time. Just a little bit on how Git works, so you understand a little bit better the problem. One of the ways that Git stores objects, well, in Git terminology, object can be from a commit to what's inside a file, or what's a directory tree, things like that. Everything, all this stuff can be stored in a thing that is called a pack file, that you can think of it of a tarball or a zip, that all the objects are inside. And it uses a lot of ways to make it smaller. One of them is compressing all the objects. All the objects are compressed with zitlib. But the other thing that it does is that you can store objects in a delta fashion. So you can store only the difference from another object. So imagine that you have two files and you have some modifications to the file. So instead of saving the two versions, you have one full version and then only the difference from the previous one. The problem here is that you can have chains of that. You can have a delta of a delta of a delta, and 50 times. So this makes it a little bit slow, because to get an object, you have to get the parent and the parent and the parent, and reconstruct all the chain and so on. So it's sometimes it's a little bit slow. So I'm going to talk to you about two of the solutions we're working on. One of them is squash tables and filter pushdown. These are two things, but they are very related. In this query, what I'm doing is getting all the repositories which latest commit is made by me. So it's a pretty simple one. But in the graph here, you can see that we get all the references from all the repos and do some filtering on them. And we do the same with commits. We get all the commits from all the repositories, from everything, and then we do some filtering. And we end up with a really small fraction of the objects that we really need. And that's really bad because we are reading too many objects that we are going just to throw away when we filter. So to fix this, we have these two things. This blue thing is a chain of iterators. The thing is that our data model is in Git data model has these properties, like a repository has some references, and the references have some commits, and commits have some trees, and so on. So the thing is that if we filter something in repositories, the next iterator, we can just skip the repositories that are not filtered, that doesn't match the filter. The same thing with commits. We don't need to go through all the commits. We can go only on the commits that belong to some references that we have filtered out, and so on. The other thing is the filter pushdown. That is this thing that is here. The thing is that we can tell the tables to retrieve only the objects that we really need. So instead of iterate over all these things, you can say, give me the object A, B, and C. And that means that it's only going to get 3 of them and not hundreds of them. So with these two guys working, this is the same query. We can do a filter pushdown that says, OK, give me only the references that the name is head. The good thing is that table is able to retrieve only that. So it retrieves only the references that with that name. And then the squash table kicks in. So when it goes to commits to retrieve the commits, it will only retrieve the commits that belong to the references that we got before. So in a more graphical way, we're converting this thing that we have before into a virtual table that knows how to retrieve only the references from here and only the commits that belong to these references. So we are getting much less objects and consuming much less CPU and IOPS than before. The next thing we are working right now is indexes. One thing that we've learned from Engine, that's the current technology that we're using, is that there is not a silver bullet to accelerate things, because everybody that uses this technology and these frameworks are searching for different things. So an index that works great for one doesn't work great for another. So it's something that it needs to be flexible. Also, the thing is that indexes can occupy a lot, and we cannot just index everything and just call it a day, because it will happen. And they take a lot to generate, so they have to full scan everything, get all the objects, and generate those indexes. So the indexes in Gitbase are defined by user. When you fire up Gitbase, there are no indexes. It only knows about repos and so on. The first implementation that we are doing right now uses bitmaps, because for us it's more flexible, and you can use it better for the current use cases. But it's something that we are not going to stop here. Probably we'll need another indexes for other jobs. You also use this key value store to map positions in the bitmap and the values. We use the MySQL index creation with some changes, so it's not totally alien to people creating the indexes. And the first test that we've done is around 2 orders of magnitude faster in some queries. There are some other queries that maybe is slower, but that's where the ballpark is. And this is still in development, so if you want to try it, you've been warned. Also, I'm going to show you some examples on what you can do with this tool. In this query, the most important things, what it's doing, this query is getting the number of functions. Well, it's getting all the files from the tip of the repository, all the files that have a language go, and counting the number of functions defined in that file. So you can, so it's a way to get complex files, for example. The interesting part here is these two functions. Language, that is the one that is able to analyze the file and retrieve which language was it made with. And then this other one is this UAST. That what it does is it parses the file contents and generates the abstract syntax tree, the tree of the source code. So you can analyze it. This function gets the contents, the language. You have to pass the language that's going to use to parse it. But then you get the next path. The thing is that this generates a tree, and the way that we have to do queries on this big tree of the source code is with XPath. This one is telling, get me any node that is a declaration and it's a function. That means give me all the function declarations from the file. And then we just count it with array length. So this is the output of the query. We get the repository, the file path, and the number of functions from it. So, for example, with this one, you can see that blobs and commits maybe are the most complex files that maybe you want to tackle. This is very easy one. I just wanted to show you that we can use natural joins. When we created the tables and the columns, the naming was also thought to be very easy to use with natural joins. So you don't have to do a lot of inner joins between a lot of tables to find what you want. You can use natural joins, and that's it. And this is the result of the query. So going back to what we are right now on the architecture, you remember that we had this Spark cluster with the driver, some nodes, and then some storage and the workers with the repositories and so on. So what we are doing and what we expect to do when Gitbase has 100 of the functionality is to just take out the storage from here and use Gitbase, call Gitbase to get information that we were getting before. This let us continue using this framework and this way of doing things because it was working fine before. But the good thing is that you can use Gitbase. You can plug Gitbase in more parts. We can plug it here, but we can have another software that also needs to retrieve information from Git, and we can just call Gitbase to retrieve that information. And that's it. The thing is that if you want to download the software, we have releases, every 2 weeks or so with new features. You can go to Gitbase. If you're interested in creating a database in Go, SQL database in Go, you can go to Go MySQL server and read about it, and maybe play with it, create your own data sources. And if you are interested in reading Git or managing Git from Go, you can go to Go Git repository and take a look. Thank you.